bomb calorimeter experiment. Little introduction, the power bomb calorimeter is used to measure heat released by combustion in a chamber. The chamber is submerged in water. The water's change in temperature is measured, and then that information is used to mathematically back out the thermal capacitance of the system. Our objectives are to become familiar with the operations and analysis associated with a bomb calorimeter, determine thermal capacitance of the calorimeter, and we also want to determine the gross heat of combustion of the samples provided. A little bit of theory, going back to the first law of thermodynamics, you have the heat transfer is equal to mass times specific heat times the change in temperature. That's going to be the base formula we use to figure out the fuel used in our experiment. It could be rearranged to MCV, which is equal to the thermal capacitance. We need to make sure not to forget about the heat added to the system by the ignition wire as well. It's not just the fuel adding, it's the heat to the system. Here's our apparatus. We have the bomb lid sitting on top, it's 1. Going through the bomb lid, we have the inlet check valve is A. We have the bomb pressure release valve is B on the right hand side right there. We have the electrode terminals going through at C. Those feed to the ignition wire seen below, which is F, and then the crucibles down there are holding our combustible liquid, and that's going to be at E. A little bit more, we have the igniter, the stainless steel bomb sitting in a bucket of water. In that water you have your stir spinning around, making sure that the temperature distribution doesn't have any large gradients. As far as the procedure, we want to measure out 10 centimeters of wire. We want to place the fuel sample, in this case benzoic acid, in the crucible, no more than 1.1 grams. We want to connect the wire to electrodes, making sure that the ground is not ground to the crucible. After that, we're going to add 1 milliliter of distilled water to the bottom of the bomb. We don't want any of that to go into the crucible. We're carefully going to secure the lid to the bomb, not disturbing the fuel sample. And then we want to pressurize and depressurize it. We're going to pressurize it up to 30 atmosphere, release the pressure, repeat that one more time, and then we're going to pressurize it up one more time to 30 atmosphere. And then once the bomb's prepared at that point, we're going to fill the bucket that the bomb's going in with 2 kilograms of water. There's a filling line on it, so we should be able to just look at that and fill it up to that line. And then we're going to place the bucket in a calorimeter jacket, ensuring that it's touching the ground button in the center of the jacket. As far as the instrumentation preparation, we're going to start the computer and open up bombcal.cfg. We're going to insert the thermocouple plug into slot 1, and then verify the temperature is reading correctly by holding our hand on it and watching that the gradient is correct. We're going to place the thermocouple in the positioning bracket of the calorimeter lid, and then we're going to ready the data acquisition system. We're going to record approximately 2 minutes of baseline data with nothing going on, and then we're going to start the experiment and run it for another several minutes. And in these 3 slides, the preparation of the bomb, the preparation of the bucket, and the preparation of the data system should be able to do it done concurrently, saving us time in our experiment. Once this part's done, we're going to lower the bomb into the water bucket. Again, being careful, making sure not to disturb the fuel sitting in the crucible. We're going to make sure that there's no bubbles coming out of the bomb, so it has an airtight seal. If there is any, we need to inform our TA. We want to connect the electrical leads of the bomb terminal, and then place the jacket over the entire unit. We need to check the leads for continuity, looking for 0 ohms, and then we're going to position the lid, ensuring the stir and thermocouple are submerged but not in contact with the bomb. Once this is done, we can place the belt drive from the motor to the stir and turn it on. At this point, we're ready to run our experiment. We're going to start our experiment log. Like I said before, recording 2 minutes of room temperature data. Then we're going to press the ignition button, and again, check for continuity. We're going to take data for several minutes, waiting for equilibrium. We want to take data up into the point where it stops raising in temperature, but not to the point where the temperature starts falling again. And then we're going to save the data and repeat the experiment with an unknown fuel sample. For shutdown, we want to turn off the stir motor and remove the belt drive. We're going to remove the lid from the calorimeter, disconnect the bomb, and remove from bucket. And we're going to depressurize the bomb by using the relief valve. After that, we're gonna open the bomb, and we need to make sure to measure the length of unburnt wire, and that's gonna go into our calculations so that we can account for the heat added to the system by the wire igniting. And then we're gonna clean out the experiment and return all items. Some expected results, using equations from slides 4 and 6, the thermal capacitance of about 8.368 joules per degree Celsius. The thermal capacitance of the stainless steel is about 1.5 joules per degree Celsius. Therefore, the thermal capacitance of the systems, just adding those two together, get about 9.868 joules per degree Celsius. The heat of combustion for about a gram of benzoic acid is roughly 26.38 kilojoules. Therefore, I predict the rise in temperature in 1 gram of benzoic acid to be about 2.673 degrees Celsius. Some sources of error that we need to look out for is the thermocouple, the measurement for the fuel, an imperfect air mixture in the bomb, and a resolution error of the oxygen regulator. And that is it.